In this video lectures, we like to discuss about the image enhancement in frequency domain, which is the new chapter, which is chapters number 4. However, in this semester, I have decided to not include this chapter in your course, meaning that this chapter will not include in any assessment, including the final exam. However, we need to discuss about this chapter. I will discuss about this chapter a little bit because there's some component that actually is needed inside some component inside this chapter is needed for the next chapter, which is image restoration. Okay, because later when we discuss the chapter 5, okay, which is image restoration, we also need to familiar with frequency domain, okay, doing a process in frequency domain. So that's why we will discuss this chapter for the purpose for the sake of understanding the frequency domain, and then you know and you understand in the things that we'll discuss in the next chapter, which is chapter 5. Okay, now let's go to this whiteboard because I already list up all important things that you need to know in order for you to prepare yourself for the next chapter, which is image restoration, because a part of image restoration also involve frequency domain. Okay, just recap back about the frequency domain. Okay, you have been exposed to frequency domains in the previous class, okay, in the previous course. Okay, I know that you already know about the frequency domain in one-dimensional signals, okay, that you have discovered in the previous course. Okay, if you remember, in one-dimensional signals, doesn't matter is it a continuous or analog signal represented by xt, or xn, which is represent your digital one-dimensional digital signal. If you want to change into this one is in time domain, okay, but if you want to change it into frequency domain, then you need to apply what we call as Fourier transform. Then you can produce your input signal in frequency domain. Okay, in general we always use a capital letter to represent the frequency domain, just to differentiate between this domain and time domain. So this terminology actually is similar to our two-dimensional signal, which is our image. Remember, in image, when we talk about, however, for image, if you need to remember that in image we don't have time domain anymore. If you talk about two-dimensional signals, okay, there's no time domain anymore. What we discuss is more about the space. So that's why now the time in one-dimensional signal will become space in two-dimensional signal. So that's why we use the word spatial there, spatial domain. So this is what we discussed earlier in the previous chapter, which is image enhancement in spatial domain. And then this domain also, you can also change into frequency domain. Okay, again, this is our fxy. If you want to change it into frequency domain, that is represented by capital F there. Again, the capital F we use because we want to differentiate between the frequency domain and spatial domain. And then if you realize that even the index there is having changed, this one is a spatial. Sy represent the index of spatial domain, while uv represent the index in frequency domain. And to convert from spatial domain into frequency domain, then you need also apply the Fourier transform. But right now we don't it just not Fourier transform. Actually, it's a two-dimensional Fourier transform. Sorry, it should be two-dimensional Fourier transform. Okay, so let's go to the slide there. Okay, that is what have been discussed in the slide, but I don't discuss all. Okay, talk about the Fourier transform, and then this is the formula for Fourier transform in two-dimensional signals. Okay, it's similar to one-dimensional signal. The difference is just now we have a double summation symbols there to represent two-dimensional signal, and this one is inverse Fourier transform. This one is for the purpose if you want to change from the frequency domain into time domain back, then you need to use the inverse Fourier transform. Okay, so the rest is just some hand calculation how to do the apply this Fourier transform formula for two-dimensional signal, but this one is not included into your in your final exam or any assessment. Okay, you just can read through there. Okay, now let's go back to our whiteboard. Okay, another things that you need to remember about the frequency domain, okay, is about this regarding this one. Okay, if you remember, if you want to process something in time domain or spatial domain, you always do the convolution process, okay, between your input image and your kernel or your filters there in order for you to produce your output. So if you do the same operation in frequency domain, any convolution process will become multiplication in frequency domain. So this is also happen for two-dimensional signal, okay, which is this one. Okay, this one, if you remember in the previous chapter, we talk about the smoothing operation. Okay, if you want to do the convolution, two-dimensional convolution in spatial domain, if you change it into frequency domain, that operation will become the multiplication. Okay, so the third line there, I just rewrite the second line. However, I change my W with my H. Okay, don't confuse with that, because most of my slide there after this, you will see more expression in frequency domain in this way rather than this way, meaning that now we are using the H, we don't use the W. Okay, but don't confuse, the thing is same, because in frequency domain we talk more about the filter, so that's why filter, when we talk about filter is something which is can be notated by the letter H there, because we get this we inspired it from the one-dimensional signal, which is H there. So that is the reason why we are using H there in frequency domain. Okay, but actually they are same thing. Okay, but just don't get confused. Later you will see that most of my slide we talk about frequency domain, then we are using the H there. Actually H and W is the similar thing, is the same thing. Okay, that is about the convolution. Okay, convolution will become multiplication in frequency domain. Now about this H. Okay, in this one more, okay, if you talk about the frequency domain, okay, the common filter that we always see is these two. Okay, actually there's more filter, but this one is the example of filter that involved in frequency domain, which is low pass filter and high pass filter. And again, you can see there, this is the shape of the low pass filter in one-dimensional signal. Okay, you have covered this one in the previous course. And again, I will like to highlight this one. This is the block diagram of each and every process in if you talk about the one-dimensional signals. Okay, and then if you convert into, of course, this one, if you want to convert into Fourier in frequency domain, then you need to apply the Fourier transform, and then it will become the capital X there. And then this filter over here is already in frequency domain, which is this one. This one is already in frequency domain, low pass filter. Or you can also if you implement the high pass filter here, it become high pass filter. So it depends which filter that you use. So and then the thing I will like to highlight, why this low pass filter shape look like this. Again, if you remember, if you want to produce Y over here in frequency domain, you need to multiply between your filter H and your X. Okay, it's not convolution anymore because this is in frequency domain. So in other words, if we talk about the low pass filter characteristic here, the ideal low pass filter over here, anything which is, if this X input image consists of, if the input signal over here consists of low frequency component, which is low than cut off frequency FC over here, it will multiply with 1 because this is 1. But if this component, where the frequency component inside this input signal over here is more than cut-off frequency, it will multiply with 0. So that's why the produced Y over here is only obtain the low frequency component of X, and it will not obtain the high frequency component of X because the high frequency will multiply with 0 over here. So that's why if your H over here is low pass filter, actually it will only allow the low frequency component of X pass through this block and stop all the high frequency component to be passed through this block, okay, by having this multiplication operation. Okay, so same goes to high pass filter, which is in contrast with your low pass filter. Anything more than cut-off frequency, it will multiply 1. Anything lower than cut-off frequency, it multiply with 0, meaning that it will only pass all high frequency component from X into Y, while stop any low frequency component in X to pass through and obtained by this Y over here. So that's why this is how the ideal high pass filter look like, and this is how the ideal low pass filter is look like. Okay, and again now let's go to so how about so this is one dimensional signal. Then how about our how actually the low pass filter ideal low pass filter in two dimensional signal look like? So that's this one, you can refer to our slide, which is this one. Okay, this is the ideal low pass filter in two dimensional signal. So why the shape is look like cylinder? Okay, you can imagine from the one dimensional signal. If the one dimensional signal low pass filter ideal we talk about the ideal low pass filter. If the ideal low pass filter of one dimensional signal is look like square, then again if you imagine the in two dimensional signals, okay, the low pass filter, then it will become again, if you talk about the two dimensional signals, then you will have it's not small h anymore, it's a capital H. Then you have the UV index to represent the coordinate or index for a frequency component, because we are not using the XY anymore if you talk about the frequency component. Then again if you try to do the terminology from here, now the cut-off frequency might be around here. Let's say this is your cut-off frequency. Okay, this is our FC. And then in order for you to this is where the frequency is 0. Same goes to this one. Okay, this one, the 0 is over here, then the 0 should be over here. So anything that close to 0 is a low frequency component. So of course the cut-off frequency should be at this line or at this border. So this is also another FC. Okay, it's a cut-off frequency. So in other words, if you want to have some ideal low pass filter like this in 2D, then you need to have some cylindrical shape. Okay, meaning that anything anything inside this circle will become 1. Anything outside this circle will become 0. Okay, so meaning that any signal, any low frequency signal, we talk about the low frequency component, it should be close to 0. This one is 0, so any point around here is close to 0. So meaning that that's a low frequency component. So anything any low frequency component should be multiplied with 1. So if you talk about the point outside here, okay, let's say this point over here, all this point is actually is far from the 0. So if this one is far from 0, then this is the high frequency component. So meaning that anything, if you talk about low pass filter, anything outside this circle should be multiplied with 0. So that's why if you talk about, if the low pass filter in one dimensional is in square shape like this or rectangle shape like this, then in two dimensional it look like this cylinder. It's a cylindrical shape there. Okay, so that is how we take try to relate between the low pass filter, ideal low pass filter in one dimensional signal and ideal low pass filter in two dimensional signal. However, one thing that I would like to remind, in two dimensional signal they are not using this FC anymore. Okay, FC is only used, FC is a cut-off frequency for this one. Okay, but in two-dimensional signal they are using the what we call as a D naught. Okay, D naught is a distance from this point to this one, this border. Okay, we call it as a D naught. The distance is D naught. So why we the distance or the radius, okay, the radius, they use the term radius. So why we use the term radius again? To measure this FC, of course you measure from 0 to here. This is our FC. So that is from that terminology. If you talk about the two-dimensional signal, then actually is also, if you talk about the cut-off frequency, actually is a radius of that circle, or the radius of that cylindrical shape. Okay, so that is actually our cut-off frequency. So that's why if you refer to this slide, now they are using the D naught. Actually D naught is FC, is a cut-off frequency for two-dimensional low-pass filter, for two-dimensional version. Okay, cut-off frequency version, cut-off frequency of two-dimensional signal version is called D naught, or in other words they use the word radius. They don't call FC anymore, or cut off frequency FC anymore. Okay, that's why you see here they use the word radius. Okay, it's the same thing, you don't have to worry about that. Okay, so that is how it's look like. Okay, now another things that I would like to highlight here is, if you talk about applying again, one thing I would like to remind you is that when you want, okay, again, this is our image in spatial domain, and then if you want to apply the low pass filter for this image, you need to implement the two-dimensional Fourier transform. Okay, then you will obtain your input image in frequency domain. Then after that you can, if you want to do, if you want to filter with low pass filter, then you need to multiply. Again, it's a multiplication process with your low pass filter. Okay, let's say you are using a low pass filter over here. Okay, low pass filter, which is I can put the HLP low pass filter, which is this one. Okay, this one. Once you do the multiplication, then you obtain your GUV, which is the output image in frequency domain. So in order for you to obtain your original image, then you need to apply the two-dimensional inverse Fourier transform. Then you can obtain back your GXY. Okay, so this is how the process work for applying the low pass filter into your image. So okay, so what happened when you apply the low pass filter into your image have? This is the example how it's look like. Okay, in other words, if you apply the low pass filter, it actually will blur the image. Okay, this is your F. Okay, this is your F, X, Y, and this is your G. After you apply the low pass filter and obtain the GXY, after you perform the inverse Fourier transform, and then you obtain your GXY. If you talk about, if you multiply or applying the low pass filter with your input image in frequency domain. Okay, as a summary, okay, is as a conclusion about frequency domain. Okay, frequency domain, one of the alternative, instead of doing the smoothing operation in time domain, I'm sorry, in spatial domain, for applying the smoothing operation, or to blur the image, you can do the convolution between your input image and average filter or Gaussian filter. That is in order for you to repeat to perform the smoothing operation. But for frequency domain, the alternative way for you to perform the same smoothing operation is by applying the low pass filter into your image, because the low pass filter is also perform the smoothing operation in frequency domain. Okay, so why that happen? Okay, for that kind of thing, I will like to discuss this thing as a reason. If you, okay, now why, when you apply the low pass filter, actually it will perform the smoothing operation. If you imagine, okay, if I scan the pixel from here to here, which is I draw in this blue line, okay, then I obtain all the intensity value over here, and I plot the intensity value over here. So if I plot, roughly what I get is something like this. Why I get something like this? Because you see, because this input image is very sharp, so that's mean the changing from one pixel to neighbor pixels value is the changing there is very significant, and is very drastic changing from one pixel to another. So imagine if we plot the signals that overlap with this line, then I can imagine it's something like this. But for image which have been blurred like this, or have been performed with smoothing operation, if you scan the same line, you will find out that the changing between one pixel to the neighbor pixel, the changing is not so significant. It's a very, it's a very small changing, so it's very smooth changing. So if I plot the signals, the array that under this blue line, then the I can imagine the curve, or the signal is something like this. Okay, so in other words, if you compare between this one and this signal, you can conclude that since this ripple here is very frequent, very high frequent, so I can conclude that this one, okay, consists of strong, okay, it consists of strong high frequency component, while this one, since the ripple and the frequency of the ripple is very big there, okay, because there is very big and the changing is very big there, so I can consider this signal consists of strong low frequency component. So that is why, if you see over here, when you apply the low pass filter, okay, low pass filter, this is the image going to the low pass filter, then it will produce this one. So why is that happen? Because low pass filter will only pass the low frequency component and distort, or it will stop all the high frequency component, which is why if you see the output of the here, okay, if you talk about the high frequency component, before that, if you talk about the high frequency component, actually the high frequency component inside the image is represent the sharpness of the image. If you are removing the high frequency component inside the image, actually you are removing the sharpness of the image. So that's why when you apply the low pass filter, because low pass filter only allow the low frequency component and stop the high frequency component, that's why you are producing the image which is in smooth condition or blur condition like this. Because now this kind of image, okay, it only consists a very strong low frequency component, okay, because you are already removed the high frequency component. or in other words, you are removing the sharpness of the image. That's why it will produce a very blur image like this. So I hope that you remember this concept when you apply the low pass filter in frequency domain for image. Actually, if it will remove the high frequency component, or if the high frequency component have been removed, in other words, you also that high frequency component actually represent the sharpness of the image. So that's why the produced image after low pass filter actually is a blur image, or in other words, low pass filter is another method that can be categorized under smoothing operation, but it have been implemented, it was implemented in uh, frequency domain instead of spatial domain. Okay, so I hope this video make you understand about what happened in frequency domain, and hope you can obtain the surface knowledge about frequency frequency domain operation, which will prepare you for the next chapter.